This video aims to teach you how to make use of an ICE table. This ICE table is very applicable to the topic in chemical equilibrium. We usually use the ICE table to do calculations found in chemical equilibrium. The first example we'll be using the ICE table will be to basically help us with the calculation in chemical equilibrium. The question is as follows. In a vessel, the initial concentration of hydrogen gas, iodine gas, and hydrogen iodide are 0.75, 0.83, and 0.11 mole per dm cube respectively. The concentration of hydrogen gas is 0.15 mole per dm cube. When the equilibrium is established at 731 Kelvin, calculate the Kc for the reaction of hydrogen plus iodine to give us hydrogen iodide. This reaction is an equilibrium. An ICE table is usually used to help to perform the calculation. The ICE table will contain the initial, which is the I, which represents the initial amount, concentration or pressure. The C represents the change in the amount, concentration or pressure, whereas the E represents the equilibrium amount of or concentration or pressure. Now the E is essential in this particular question because in order for us to calculate the Kc, we will need equilibrium concentrations. This is an example of how an ICE table will look like. You could see that you can have the equilibrium reaction equation that is shown above, and you have the rows that says I, C, and E. The units are also shown. So the question tells us that hydrogen, iodine, and hydrogen iodide have the initial concentrations of 0.75, 0.83, and 0.11 mole per dm cube respectively. At the equilibrium, we are left with only 0.15 mole per dm cube. What happened here is that by simple mathematics, you would be able to deduce that there must be a loss of 0.6 mole per dm cube of hydrogen. The rho for change actually corresponds to the stoichiometric ratio that is found in the above equilibrium equation. Hence, using that information, we can actually find out what is the change in terms for iodine as well as the change in terms of hydrogen iodide. The mole ratio of hydrogen and iodine are in the 1:1 ratio. I've lost 0.6 moles per dm cube of hydrogen. Therefore, I will also lose the same 0.6 mole per dm cube for iodine. However, since the mole ratio of hydrogen and hydrogen iodide is in terms of 1:2, the change will be an increase of 1.20 mole per dm cube. Now, to find out the equilibrium concentration for iodine is simply 0.83 subtract 0.60 to give us 0.23 mole per dm cube. And to find out the equilibrium concentrations for hydrogen iodide will be 0.11 plus 1.20 to give me 1.31 mole per dm cube. Now, as you can see, that in order for the equilibrium values to be substituted into the Kc expression, we need to ensure that these values are in mole per dm cube or can be converted to mole per dm cube. It's now timely to do a summary of the ICE table so that you will be quite clear. We've seen 3 examples of how ICE table can be used. Of course, the list of questions that we can use for ICE table is really pretty much non-exhaustive. Do take note that the units of ICE table can be mole per dm cube, could be moles, could be Pascal, could be ATM. However, when using mole per dm cube in the units for the ICE table, you must be certain that the volume stays the same for the question, for the reaction. So in our earlier case, we generally use mole per dm cube in the ICE table was because we were quite certain that the reaction vessel's volume stayed the same. Are we so particular about concentration? It's because concentration can be affected by volume and can be affected by amount of substance. So if your ICE table is going to use mole per dm cube and there is also volume changes, your concentration changes can be actually due to the volume change rather than the amount of substance being changed. The second row of the IC table is quite crucial because the second row of the IC table relies on the stoichiometric coefficient, whereas we use the third or the final row on the IC table for our Kc expression calculation.